Today we're going to talk about the classical electron radius, and I'm going to talk about it in relation to the ohm particle model that I'm proposing. So I'm going to try and see where the classical electron radius fits into this model. Okay, so the classical electron radius is a combination of fundamental physical quantities, which are down here, that define the length scale for problems involving an electron interacting with electromagnetic radiation. So that is what mainstream thinks the classical electron radiation means. It links the classical electrostatic self-induction energy, E squared, permittivity and E squared. Okay, so for a homogeneous charge distribution, a sphere, to the electron's relativistic mass, E equals mc squared. Okay, so this is the part I like. According to, or don't like, I should say, according to modern understanding, the electron is a point particle with a point charge and no spatial extent. Attempts to model the electron as a non-point particle have been described as ill-conceived and counter-pedagogical. I'm going to read that again. Attempts to model the electron as a non-point particle have been described as ill-conceived and counter-pedagogical. In other words, any attempts to model electron, any attempts to do what I'm trying to do are ill-conceived and shouldn't be taught. So what I'm doing is going against mainstream because I'm trying to teach you that particles might have an internal structure, but they're saying it's ill-conceived and should not be taught. That's what pedagogic has to do with teaching. Okay, so, but then they go on to say, nevertheless, it's useful to define a length. I like the term length scale better that they use up here. It is useful to define a length scale that characterizes electron interactions. So that part I agree with because that's what I'm trying to define here. I'm trying to determine a length scale in terms of the fractal paradigm. Okay, fractal paradigm is all about length scales, and so you can have similar phenomenon in a fractal. You can have similar phenomenon happening at different length scales. And so the reason I'm playing around with this model, it's 100% to do with the fractal paradigm. I'm trying to find a set of rules that are scalable, okay, because I believe physics, if the universe is a fractal, then physics should be scalable. The laws of physics should be scalable, and that's what I'm trying to figure out here, whether that's even possible. And so, you know, I'm not really saying that my model is perfect or that it is the model of the universe, but for about 10 years now, I've been studying this and trying to figure out if I can find a way to scale the laws of physics so that each, fundamental particle is essentially the same, but the only difference is the length scale. And so that is the whole point of what I'm doing here, in case you're wondering. But today we're going to talk about the classical electron radius, which a lot of people use. Even independent researchers use the classical electron radius, and I want to see if this makes any sense whatsoever. So what I'm going to do is I'm going to take this equation here and I'm going to put it up here on a new slide, and we're going to have a closer look at this classical electron radius. Now, what you will find when you look at the literature is that there are actually other equations that also use the fundamental constants of nature and fundamental variables and constants of nature to evaluate to the classical electron radius. So here are two more as well. So all of these three pieces of code, if you want to call it that, evaluate to the classical electron radius. And so you'll notice down here that the fine structure constant, which is alpha, is in these two terms here. So in this term and this term. And so, so today, what I want to do is I want to focus on this one. Okay, and the reason I want to focus on this one is because it has a 2 pi term, and it also contains the Compton wavelength, which I am identifying as the circumference of my own particle model. And so this would be for the electron, of course, because we're talking about the classical electron radius. So this lambda term here is the Compton wavelength, which I'm identifying as the circumference of my own particle electron. It's got the 2 pi term here, which is going to be helpful, and it also has the alpha term, which is the fine structure constant. So this whole discourse that with lots of math, all my videos with lots of math, started out with me trying to decode the fine structure constant, if you will remember, or if you've seen that video, you'll know that this all started with me trying to identify the fine structure constant and trying to decode it. So this is also going to be part of the decoding of the fine structure constant. So let's have a closer look at this. This is the classical electron radius. This is the Compton wavelength of the electron, which I identify as the circumference of my electron ohm particle. This is 2 pi, of course, and this is alpha, which is the fine structure constant. So what I'm going to do here is I'm going to solve for the fine structure constant. And so the way you do that is you multiply both sides by the inverse of this term here. And so you put 2 pi over the Compton wavelength on this side. And so then you have alpha on its own. So next, what I'm going to do is I'm going to group, instead of grouping these two terms here, I'm going to group the 2 pi with the classical electron radius. And what you find is that, of course, 2 pi times a radius is the circumference of a circle. And so this basically evaluates to the classical circumference of the electron. So instead of the classical electron radius, it is the classical electron circumference, at least 2 pi r. 2 pi r is the circumference of a circle, and so this interprets as the circumference of a circle. And as you may recall from my previous videos, the Compton wavelength of the electron, at least the non-reduced Compton wavelength of the electron, evaluates to the circumference of my ohm particle model. And so technically here we have two circumferences. One is the classical circumference, the classical electron circumference, and the other is the Compton circumference, the circumference of my model. And it appears that the classical circumference divided by the Compton wavelength, the Compton circumference, is alpha. And so this is another way of looking at alpha geometrically. I'm still trying to figure out what the true meaning of the classical electron radius is, because in my model, the classical electron radius is not the circumference of my system. And so, but for some reason, the classical circumference divided by the Compton wavelength, which is the circumference of my model, is exactly the fine structure constant. So I just want to take a little aside here, and I want to, we're going to have a closer look at this term here, 2 pi times the Compton radius of the electron. And we're going to do unit analysis on it. And so here is the 2 pi times the Compton electron radius. 2 pi, as you may recall from my 2 pi or not 2 pi video, has the units of radian per cycle. And so the classical, or any radius, the units of radius, because as I showed you in the previous video, Radius is the arc length of an angle of 1 radian. Okay, so this is why I assign the radius the units meter per radian. Okay, the radius and radian are closely coupled, they're closely related. 2 pi times the radius is the circumference of a circle. Okay, and the circumference of a circle has units meter per cycle, so meter per complete cycle. So the length of the circumference of a circle is meters per cycle in modified unit analysis. And in a similar manner, the radius of a circle, which is also the arc length of a circle of an angle 1 radian, has units meters per radian. Radius and radian are closely related, which is why they're almost exactly the same word. Okay, the arc length of a section of a circle with the angle of 1 radian is equal to 1 radius, and that is why I give the radius in modified unit analysis the units meters per radian. Okay, and so here the 2 pi times the classical electron radius is a circumference of a circle, not my circle, but it is the circumference of a circle, and the radians cancel, and you end up with meters per cycle. So as I said in a previous video, the units of the circumference of a circle are meters per cycle in a physical system of measure. In the modified unit analysis, physical systems of measure. And so that is how I map that out. I know someone emailed me complaining about my tangential velocity because I had a radius in there, and I didn't exactly show you this. So I thought it was important to bring this up right now. So this is an important point. The units of the radius of a circle is meters per radian in modified unit analysis. Now in modified unit analysis, I do everything in the domain of the cycle. And so radians tend to cancel out. They are intermediate units. They're there, but they cancel out, and you end up in the domain of cycle. And so I want to make sure that you're clear on that the units do in fact balance. The radians cancel, and you end up with meters per cycle. So now when you look at the equation that I derived earlier with the classical circumference divided by the Compton wavelength, or circumference of my own particle system, is equal to alpha. And now you can see that the units of 2 pi times the classical electron radius is meters per cycle, and the units of the Compton wavelength are meters per cycle, and of course these are going to cancel, and alpha is unitless. As we all know, it is unitless. And so why is alpha unitless? What does the unitless value mean in a system? Well, in the systems that I develop, when I find a unitless value in my code, if I find something in my code, it is usually associated with a calibration error, a gear ratio, or a bug. So let's say, for example, I'm building a robotic system, and the engineers build the system, and it's got gear ratios and motor controls, etc. And so they give the system to me, and they give me all the specifications, and I write the program, and I run the motor, and the motor is supposed to go 2 centimeters, but it goes 1 centimeter. And so it goes half as far as I expect it to go. And so in order to fix the problem, I have to maybe send twice as many pulses to the motor to get it to go 2 centimeters instead of 1 centimeter. But I don't know why. I don't know why I have to do this, because the specifications said that I need to, told me what the gear ratios and everything were, and so I would send a certain number of pulses, expecting it to go a certain distance, and it doesn't go as far as I want. So I need to send twice as many pulses to get it to go the distance I want, but I don't know why. And so in a similar manner, we have to plug alpha into many of the equations, but we don't know why. And it's a unitless value. Gear ratios are unitless values as well. So in my system, it's more likely that we were sent the wrong motors, and that had the wrong gear ratio, and that would explain why the motor didn't go as far. And in reality, we should send the motor back and get the one that we expected. And so, I mean, that's just an example. Actually, that's an example that actually happened to me, but that's an example of a unitless value that I might have to plug into my software to get the software to work right, but it doesn't, explain what the actual problem is. And so that's kind of how I'm seeing alpha here. It seems to be, because it's a unitless value, it seems very suspicious to me. And so that is why I'm trying to decode alpha, because I'm trying to figure out, why do we need to plug a unitless value into our equations to get a result that we expect. So this equation here can also be written in terms of radius. So right now I've written it in terms of circumference, what I call the classical circumference, and the Compton wavelength, which is the circumference of my own particle system. But you could also simplify it and write it in terms of radius. So we can write it in terms of the actual classical electron radius divided by the circumference divided by 2 pi, which gives the radius of this circle, which also happens to be the charge separation of my own particle model. And so when you take the classical electron radius and divide it by the, if you want to call it the Compton radius, or the radius of my own particle system, and or the charge separation of my own particle system, you also get alpha. So this is actually a lot simpler to think about than circumference, although I wanted to try to be consistent with everything I do. And in the previous video, I did everything in terms of circumference. If you want to do it in terms of radius, you divide both of these things by 2 pi. You divide this by 2 pi, and you divide this by 2 pi. You get the original classical electron radius divided by what would be the reduced Compton wavelength. The reduced Compton wavelength, which is the Compton wavelength, the circumference of the circle divided by 2 pi, to get the radius of this circle of my system. And so this is actually much simpler to look at, and so it could also be written like this. So on the Wikipedia page for the fine structure constant, there are a whole bunch of physical interpretations of the fine structure constant. And so there are a whole bunch of them, too many to talk about here, but I did find one that seemed to be related to what I just derived right here. And so basically what it's saying is, and it's more about the magnetic moment than it is the fine structure constant, but as I showed you before, the magnetic moment is really alpha divided by 2 pi. And so here it says the magnetic moment of the electron indicates that the charge is circulating at radius rq with the velocity of light. So this really got me thinking, because this reminded me a lot of the tangential velocity that I talked about in the previous video. And so in my own particle model, the tangential velocity of the system is the speed of light. So here it says that this radius rq has the velocity of light, and it said it generates the radiation of mc squared, the radiation energy of mc squared. And so basically it's related to the energy of the mass of the particle and has angular momentum, blah, blah, blah. These values inserted into the definition of alpha. So when they take all this stuff and insert it into the definition of alpha, you get alpha is equal to the classical electron radius divided by RQ. So this is actually what I just derived right here. So their RQ is the radius of my system. And so this is what they say next is actually really interesting. It says it compares the dynamic structure of the electron with the electrostatic assumption. So I don't know exactly what they mean by this, but basically what this is telling me is that this ratio here is a ratio of the static assumption divided by the dynamic structure. Okay, so again, I'm not really sure what that means, but I think this gets me closer to understanding what alpha is in the context of my own particle model, because my own particle model obviously is a dynamic model, not a static model. So I think it's possible that alpha is a calibration error, is a tweak that converts from the static assumption to the dynamic structure, to the dynamic assumption, because I'm assuming a dynamic system here and mainstream assumes a static system. And so it's possible that alpha is just a conversion factor from the static assumption to the dynamic assumption, and or vice versa. So that is as close as I've gotten so far to a physical meaning of alpha in the context of my own particle model. So I want to try and tie this all together by bringing Planck charge back into the mix. Okay, so what I found was when you take Planck charge and replace E squared with Planck charge squared, when you replace elementary charge with Planck charge, then you end up calculating this value here. So when you take Planck charge squared and plug it into this equation here instead of elementary charge, then you end up with this value here, which is in fact the Compton wavelength of the electron. And so, when you plug, so Planck charge is obviously related to the Compton wavelength, because when you plug Planck charge into this equation, you get exactly the Compton wavelength. So I found that quite interesting. I think this is an important piece of the puzzle. And of course, the Compton wavelength is the circumference of my electron particle that I have previously defined. And so tying this all together in a nice simple way, we've got the classical electron radius divided by the Compton wavelength or circumference of my own particle is equal to elementary charge squared divided by non-reduced Planck charge squared is equal to alpha over 2 pi, which is alpha over 2 pi is the anomalous magnetic moment. And so this little chunk of code right here is very interesting. I think a lot can be learned from just studying this little piece of code right here. I find it really interesting, and so everything is in here that I find really interesting, including Planck charge, 2 pi or not 2 pi, that is the question. We've got the fine structure constant, we've got the circumference of my own particle system, elementary charge, and classical electron radius. And so, like I said, this little chunk of code is quite interesting to look at and study. And in order to try and to determine whether the system I'm developing makes any sense, to try to make sense out of the fine structure constant and the anomalous magnetic moment, which is fine structure constant divided by 2 pi. So that's about it. I think I'm going to leave it at that. I'm sure I've given you a lot to think about. I still have a lot to think about. And so with that in mind, I guess I'll be back.